We're going to have to keep the time. Normally, we would keep going sometimes until 4:30 with questions, but we can have a few questions at the end, but we're going to need to keep the time because from 4 to 5, we've got a meeting with the dean. So, who's the person who actually does the hiring. So, anyway, yeah.
So, welcome to our Friday colloquium. We had a colloquium lately, so I'm going to introduce our speaker, Dr. Kevin Hainline. He's an astronomer at the University of Arizona who studied how first galaxies form in the early universe. He received his bachelor degree in physics from Hainline College in 2006, PhD in astronomy from UCLA in 2012, before joining Dartmouth College as a postdoctoral researcher. He later moved to the University of Arizona, where he's currently an associate research professor. As a member of the James Webb Space Telescope Advanced Deep Extragalactic Survey, JADES, he works to identify and understand some of the most distant galaxies ever observed. His research also spans active galaxies and discovery of ultra-cold brown dwarfs in deep extragalactic datasets, bridging studies of the early universe with the structure of our own Milky Way. He is also an active science communicator who enjoys bringing the story of the universe to larger audiences.
Yeah. Thank you so much. I really appreciate you all bringing me out. I'm Dr. Kevin Hainline. I'm visiting from the University of Arizona, as was just said. I've been there for about 10 years in Tucson, and I'm really happy to be here because the weather is like really perfectly pleasant. So thank you so much for setting that up for me. I want to talk to you today about galaxies. And I'm excited because it's like one of the first time in human history where we can start talks by saying that I want to talk about galaxies from the beginning of the first galaxies, from the beginning of time, from the first 300 million years after the Big Bang. Because like prior to JWST, prior to the last like 5 years, every person who would talk about this would talk about it theoretically. But for the first time ever, we're able to talk about this not just from a computer simulation or, well, these are probably out there, but from an observational standpoint. We're going to talk about really, really distant galaxies, how they form stars, how they assembled their mass, how they made themselves more complex. And this is a talk that's going to focus on my work, understanding early galaxies, and at the end I'm going to kind of lay out my vision for my future research as well. This is entirely made possible by the JADES collaboration, of which I'm a key member. JADES is an international collaboration of scientists who worked on the main camera and the main spectrograph, NIRCam and NIRSpec, on board James Webb, so on board the JWST. And they were given essentially like about 800 hours of combined time by virtue of building the instruments to build this incredible survey. And you can go to this website, don't do it now, listen to me now, but at the end, you can go to this website where you can actually explore the data because the data is all public now. You can explore it all yourself. You can essentially say, I don't want to hire Kevin, we'll just use the data already. It's all there. And I did a huge amount of work as a member. I'm the person on the team who figured out the distances to every one of the galaxies. I'm also essentially the librarian. Every time one of these team members sees something weird, they message me, Kevin, have we looked at this? Has someone looked at this? What's this? What's going on here? And I'm the person who looks at I've looked at so many galaxies. In the world right now, I probably have looked at more galaxies in JWST data than any person alive. I'm going to start with this, which is there, but this is a special version. This is a great way to start a talk about the early universe, because we're in a room filled with people who might wonder, why would you care about galaxies from the beginning of time? Or why would we care about astronomy at all? Or why would we care about things that happened a long time ago? And we start with this. This is such an important diagram that I've been in no less than 3 rooms that have this on the wall today. Right? You see this all the time, right? You see it all the time. But the thing is this is a triumph of human ingenuity. The fact that we were able to discover the building blocks of the natural world and organize them. Right? If you are someone who has never seen this before, this is the periodic table. Every one of these boxes is a different element. You're very familiar with some of them, most of the ones that near the top and over on the right. But you can see here you got hydrogen and helium and lithium, beryllium and boron, carbon, nitrogen and oxygen and fluorine. Yeah, this I can go on, but like this is actually I can't. That's where I limit my limit. But these are all of the things that everything is made out of. And I like this version because every one of these is colored by how it was formed. You are made of materials that were born at the beginning of time as light, and that light became particles, and the particles inside of stars were pushed together inside of galaxies. And so things like Big Bang fusion here only made hydrogen and helium. Everything else happened afterwards in merging neutron stars, exploding massive stars, dying low mass stars. So look, you see this oxygen's green? It's exploding massive stars. Right now you are breathing things, oxygen gas, that only existed because a star lived its entire life and died. And in that explosion of that star, atoms were put together that now you are breathing. And how do we know this? Well, we know this because we can take pictures of this happening. We can see this happening live. So the motivation for my entire talk is, man, it'd be really cool if we could actually watch this process happening. And to do that, we have to look back in time, all the way back to the first stars and the first galaxies, so we can start watching and seeing. Because if this is true, then if we look far enough back, we shouldn't see some of these elements. We should see simpler and simpler galaxies, simpler and simpler gas, right? But this is something where, you know, you see these, like, it's printed on like throw pillows and stuff, like, we're made of stardust. People put them on their Instagram, TikTok, look, we're made of stardust. And I'm telling you, we know this and we see this. And it's not just stardust, it's star explosion. It's star death. It's the end remnants of dead stars spiraling in to just make things like my wedding ring here in silver. It's really amazing. I think this is a wonderful way of depicting this idea, right? And to do this, to explore how these things come to be, we use pictures like this. This is a very famous picture called the Hubble Ultra Deep Field. It's from the mid-2000s. Some of you, the more that I teach, the more that I realize, some of you were born after this was taken, which that makes me feel crazy sometimes because that's how time goes, I guess. But this image changed my life. Because I remember seeing images like this and the Hubble Deep Field, which was the Hubble Space Telescope opening up its shutter and taking hour-long exposure, many hours-long exposure of this one chunk of sky, a tiny chunk of sky, a grain of sand at the end of your arm chunk of sky, and it was filled with these little smudges that we call galaxies. And today we're going to talk about galaxies, which are the homes of stars. We're going to talk about how galaxies have different shapes, and different properties, and how we measure that. But more importantly, we're going to talk about how an image like this can tell us about the history of that periodic table, which is, by definition, the history of how you came to be, how we came to be here, right? So the first thing that's important about this is that when you look at a picture like this, because light travels at a finite speed, the farther something is away, the longer it's taken for light to get to us. The sun is 8 light minutes away, so the light from the sun takes 8 minutes to get to us, meaning if the sun were to blow up, we wouldn't know about it for like a blissful 8 minutes. And then eventually, we could see the sun explode, and someone would be like, the sun just exploded. And you could be pedantic and say, no, the sun exploded 8 minutes ago, right? Like, and if it were like galaxies are like millions of light years away, like the Andromeda galaxy is 3 million light years away, which means that we're seeing it as it was 3 million years ago. And so this image, the farther ones in the image are actually farther back in time. If I took a human version of this, it would be like a picture of a crowd, but every farther row is like, oh, this is a row where everyone's from the 1960s. Oh, this is a row from everyone in the 1920s. Oh, this is a row where everyone's from the 1800s. On and on and on and on, back farther in time. That's great, because as I just said, I'd love to see these processes happening in the early universe. I can take pictures of it. Historians would love to do what astronomers can do. There are historians here at Fresno who are like, I'm an expert on ancient Rome, and I can go, and if I told them I have a camera that could take a picture of ancient Rome, they would pay me so much money for that camera. And we have cameras that can take pictures of the ancient Rome, the ancient galaxies. What I want to focus on is what we've learned about the universe from the first billion years in the history of the universe. Here is a diagram that was put together for National Geographic by me. And it is a diagram showing the history of the universe. It was in a special space issue from a couple years ago. This is the whole universe, where today, 13.8 billion years ago, and I'm showing just the first 1.5 billion years zoomed in. I will tell you, we live in an exciting time in human history, sometimes too exciting, but in terms of universe history, we live in an incredibly dull time. Because the first billion years of the history of the universe were the most exciting time. If you're a person who suffers from like FOMO, where you're like, oh man, you should fear that you missed out on all the good stuff. The first galaxies, the first stars, the time when the universe was making hundreds and hundreds of stars for every galaxy, every single year, the first supermassive black holes. All this happened. The Big Bang, 13.8 billion years ago, produced hydrogen and helium. That hydrogen and helium filled the universe and slowly cooled. And eventually, there was this period of time where the universe was cool enough, the hydrogen and helium were essentially just kind of in a kind of neutral state. and they just floated around. We call this the Dark Ages. The Dark Ages, this foggy period of just neutral hydrogen and helium cooling. No stars, nothing producing light. There was still light left over from the Big Bang ping-ponging around, but it was just in a neutral universe. And then it was the first stars that started to clear in a process we call reionization. Clear this fog, the first stars in the first galaxies, which produced likely the first supermassive black holes. And this all happened in this first 1.5 billion years. You get these galaxies that aren't the big spirals like we have with the Milky Way, but little nuggets. We're going to see pictures of these galaxies. Little nuggets coalescing to form these larger structures to eventually start to form the first disk galaxies. And we finish this process of reionization and clear the universe's fog, leaving the kind of populations of galaxies like the Milky Way was when it was first born. And again, up until just 5 years ago, all of this was theoretical. And now I can actually show this process going on, right? So the first 1.5 billion years is really important. The first stars, the first galaxies, the first supermassive black holes, and this process of reionization. All of this happening now. And that is the focus of what I do research on when it comes to the high redshift universe. So Hubble did a really great job of showing us peering into this first 1.5 billion, first 1 billion years, but it was limited inherently. This was the farthest galaxy that Hubble had confirmed. It's a galaxy called GNZ11. And GN stands for Goods North. Goods is a region of the sky that has been studied by many telescopes. Goods is the Great Observatory Origins Deep Survey. It was like, let's get a bunch of telescopes to all look at this one patch of sky very deep. Therefore, we can look at it as different wavelengths of light. And this was the farthest one found, this little smudgy galaxy right here. GNZ11. Now it's a redshift of 11. What does that mean? Well, redshift is a number that indicates how far away the galaxy is. But this one is probably 440 million years after the Big Bang. That's how far back in time we're looking. We're seeing the galaxy when the universe was less than 500 million years old. Right? So if I were to go back this one slide, right? So that puts us just right over here. So GNZ11 is actually right there. This is GNZ11. Like, we're in the process of clearing this out. But like, gosh, it's not one of the first ones. There's still first galaxies. This is, still 500 million years after the Big Bang. And GNZ11 was one of the farthest galaxies primarily because Hubble couldn't see farther. The reason I use this word redshift is because all the light, as we're going to talk about in a second, all the light from a galaxy is shifted to longer wavelengths as you go to farther and farther back in time, as you go to farther away. And Hubble could not see galaxies farther than this, no matter how long Hubble could stare. Here's a diagram that I put together where I show redshift here, but also on the top, if you don't want to think in redshift, here's going back in time. This is 700 million years after the Big Bang, 650, 600, 500. So the Big Bang's off to the right. 450, 440, there's GNZ11. And then this is how bright the galaxies are. Not how bright we see them, but how bright they intrinsically are. How bright? So like the ones up near the top, really bright, down here pretty faint. And what I want you to see is that as you go to farther and farther distances, Hubble could only see the really bright objects. This is Hubble's view on this region of sky that I study before JWST. This is a triumph of human ingenuity. The fact that we can see this many galaxies and really understand them, that's a really big deal. This took many, many, many hours, many, many, many studies. Researchers around the world working constantly to help confirm these with enormous telescopes like the ones in Hawaii, just to get this picture. It was really incredible, but it was inherently biased. There are galaxies, you'd think, down here that are faint and high redshift, we can't see them. And then also, it kind of cuts off here. Can't really see anything beyond that. And so, exploring these sources gave us an understanding of how the universe changed all the way up to about 400 million years after the Big Bang. But the sources were faint, difficult to follow up, and we had a very limited picture, right? So here are some questions that my research explores that kind of build off of this. These are kind of some of the fundamental questions that I look at. When did we get the first galaxies? When exactly? How quickly do these stars create the heavy elements? Was it really fast? Did we go from pristine gas to the whole periodic table overnight? Or did it take millions of years or billions of years? How did they grow? Did they grow together in clusters and groups? Were they born separately? Do we see galaxies in the early universe that are already in the process of merging, which is crazy? What sources cause the universe to change and reionize, this process of the fog clearing? And how did star formation start and stop? And to look at this, we needed a telescope that was better than Hubble. We needed one that looked at longer wavelengths with a bigger mirror, and we have that. It's called JWST. It was launched in 2021. You know, there's an entire talk about the development and launch of JWST. I worked on the main camera. I was part of testing the main instrument and also commissioning. So I was out of mission control many times for many months while testing the instrument and telescope. As part of it, you can, you know, if you're having dinner with me tonight, you can ask me all about the stories of how, while this was sitting in a test chamber at Johnson Space Flight Center in Houston, Texas, the telescope, this $10 billion telescope, a hurricane came and swept over NASA, and I was there for that. So you have to ask me at dinner for the story of that. But what I wanted to show here is this is wavelength of light down in the x-axis, and then up here is how faint can you see. So what you want is to go low, because that means you can see fainter and fainter light. And Hubble did pretty well, but Hubble was limited. Out here, Hubble couldn't really see things. The deepest it ever did is this star. JWST can go deeper than Hubble's deepest ever in just about 2 hours, just 3 hours. This is just 3 hours. It can do way better than Hubble could do at the same wavelength, because it wasn't very sensitive here. And then as you go longer wavelengths, it gets even better. You know, the Spitzer Space Telescope, you know, the deepest it ever got, we go, you know, like in just 3 hours, like an order of magnitude fainter. And the other thing is that JWST has this enormous mirror, huge 6-meter mirror, wouldn't fit in this room. And you can see Hubble's clarity, Spitzer, tiny mirror, 2 meters. Hubble, or JWST, just enormous quality of life improvement. So it's a really incredible telescope. Now let's just look at galaxies. So I want to talk, I need to take a step back, especially for those of you who don't think about galaxies very often. I have to tell you some stuff that will help you get the understanding of why we care and how we can learn things about galaxies. This is a really beautiful mosaic where they've combined images of a lot of different galaxies. They're not this close to the sky, but these are a bunch of very famous galaxies. Some people in the room probably have their favorite, you know, favorite one up here, right? Like, again, 101 is like a lot of people's favorite, very pretty galaxy. But I want you to notice when you look at these, every one of these is a galaxy. Many of them have 100 billion or so stars in them. And galaxies come in different shapes. Some are spirals. This is a spiral, but from the edge on, right? Some of them are kind of irregular, like IC 1613 here, right? And then there are other galaxies that don't have this picture, you know, up here, that like, they're kind of like fuzzy blobs. They don't look like they're blue because they don't have star formation. The color, the shape, these tell us about the population of stars in the history of the galaxy. And we can look at galaxies like this and the shapes and the colors to understand things that are going on in the galaxy, because we know galaxies are made mostly of stars, gas, dust. There are planets around the stars, but they don't put enough light for it to matter. Mostly it's the stars, gas, and dust. Those are the things we care about when we look at galaxies. Those are the things that we can measure to understand the history of the galaxy. So this is one of the more complicated diagrams, but I got to show this to you, right? This is a diagram showing if I were to take a galaxy like in the previous page and pass its light through a prism by wavelength, long wavelengths over here, short wavelengths over here, this is what its light would look like. And I've got, so brighter is up top and fainter is down here. And so what I'm showing you this is I'm also showing different galaxies at different ages. The blue lines are the young baby galaxies, and then as a galaxy ages, it goes to these red lines. So to think about this, notice that this red line down here, this is the ultraviolet portion of the wavelengths from the galaxy. There's a lot of ultraviolet light from young galaxies, but as a galaxy ages, the ultraviolet light, the stars that give off those ultraviolet light, they die. The really blue, energetic ones die first, leaving behind essentially an older population. So already, by looking at how blue or red the galaxy is in the ultraviolet and optical, I can tell the age of the galaxy. Look at that, right there. Just because I understand how stars work. Also, do you see that, like, you know, so this right here is called the stellar continuum. Is this not working? Sometimes. Yeah. This is called the stellar continuum because it's the light in general from the stars. Here, I'll take the laser. There you go. I'm sorry, my laser is not particularly great. There's a better one. Stellar continuum. I apologize for everyone. I always get excited and I'm like, I can see it. Oh wait, no. Stellar continuum, right? This is just the light from all the stars added together. But you might be wondering, why do I see all of these little like spikes? You know, what's with the spikes? Well, it turns out galaxies are filled with gas. And gas, if you've taken quantum mechanics, has this like fun property that it's got electrons around atoms. And when electrons get excited by certain wavelengths of light, they move in orbitals. And when that electron drops back down to a set of orbitals, it releases photons, light, of very specific wavelengths. You know this because you've seen a neon light. If you've gone to the planetarium, there's this beautiful little Dibber gift shop and a neon light. And that neon light is just electricity hitting atoms, causing them to what's called fluoresce, produce light at a very specific wavelength. Every time you've seen neon, it's just the process of what's going on making these spikes, and we call this nebular emission. Nebular emission. The spikes, and then also the fact that there's like a weird cliff here, that's also nebular emission, but I don't want to get into that. Mostly, every one of these spikes tells me about the chemical makeup of the galaxy. I know, don't quiz me right now, but I know what every single one of these spikes corresponds to, right? There's oxygen, over here is hydrogen, this is oxygen here, there's some neon, like all of this is oxygen right here, there's some carbon right there. These spikes are from very specific species. So here now I can tell you the age and chemical makeup of a galaxy. Notice the spikes don't appear down here. That's because to fluoresce you need energetic light. Just like you need that electricity, like you know, these galaxies are like a neon sign where there's not a lot of power going to the neon sign. You need the energy from the very energetic young stars to power these emission lines. But once that's gone, they just kind of die out. And then finally, there's this thing here. You see a cliff. This is pretty important for what I'm doing. This is maybe the most important part. If you've zoned out already, zone back in for a second, then you can zone back out. This cliff is called the Lyman break. And it has to do with the fact that galaxies have a bunch of hydrogen in them. There's a reason it's colored red and up in the top left corner with 1. It's the most abundant element in the whole universe. And hydrogen has a property, which is that it's got this little electron around it. And that electron is looking to accept certain energy. And it'll kind of fluoresce and then come back down. But also, if you hit it with enough ultraviolet, like a really energetic light, it'll just absorb it. And so all of these galaxies are surrounded by a gas that absorbs all of the super energetic UV light. And that's what you're seeing here. You're seeing that it just like drops off this cliff, which means that it is emitting this light here, but it's getting absorbed by the hydrogen. This is a filter, preventing you from seeing the light from these galaxies at short wavelengths. Because otherwise, you would ionize the hydrogen, knock an electron off into the universe. All that is to say, if you just were like, what does that even mean? Is that the Lyman break is an omnipresent thing in really, really energetic star-forming galaxies. And if you took a picture of the galaxy at a wavelength like this, you wouldn't see it. But if you took a picture here, you would. I'm going to come back to that on this next slide, which is, this is a picture. This is an example galaxy where I've shown you, like, this the same thing I just showed you with that crazy cliff, and there's all the spikes. Oxygen, hydrogen, oxygen right here, neon, all the spikes. But now, in an ideal world, would love to get that spectrum, pass the light through a prism and get it. But I can't do that. That's really, really time consuming. What I can do is I can take pictures. Every one of these right here is a picture of the galaxy at a wavelength corresponding to these little squares. And notice, I'm not showing this picture that should be right here at 0.6, 0.8, 0.9. This is Hubble filters, this is JWST filters. I'm not seeing it here. That's because it is on the other side of the Lyman break. It's invisible. The hydrogen gas around the galaxy is absorbing it. You could imagine this, like, there's a bunch of hydrogen blocking our ability to see it. And the hydrogen doesn't affect the light at longer wavelengths because it just passes right by the hydrogen. The hydrogen, like, if I was a bouncer here at the door and I was saying, like, if you come to me and I look at your wallet and you have a $20 or more, I take that out. Everyone who left this room would have $20 or less in their wallet. I would, you could leave with as much, like, oh, I got a bunch of quarters or whatever. But anytime you have more than 20 bucks, I take all of that, right? And that's what's going on. It's a filter, preventing you from getting really energetic light out of the galaxy. And as the galaxy is at more high distances, or large distances, like this is put at redshift 6, which means you're seeing it less than 1 billion years after the Big Bang. As you go to farther distances, the whole light is stretched to longer and longer wavelengths. So this is what happens. So images of the galaxy in multiple filters. We call these red points photometry. The black is the spectrum. But watch as I shift it to higher redshift, meaning the black line is going to go to the right and get stretched out. But also, watch the red points and watch the images down below. There we go. Notice it's disappearing from longer and longer filters because that break, that cliff, is pushed out such that now I can't see it in all of these filters. I can see it over here. This right here is the fundamental way that I find distant galaxies. When people ask me, I'm just looking for ones where I don't see it in all of these short filters and suddenly I see it in longer filters. Because if I can do that, I can see galaxies stretching back to within the first couple 100 million years after the Big Bang. I do that in a series, in a data called JADES, the JWST Advanced Deep Extragalactic Survey, which I talked about earlier, which is these two fields, GOODS south and GOODS north. The yellow is the JADES data. There's some extra data from other teams that we've added in that is, fills in some of the gaps and stuff. There's a bunch of great papers here. It's pretty large, but compared with other surveys that are much shallower, it is small. It's still a pencil beam. But compared to other JWST surveys, it is the most comprehensive, the most filters, the deepest. It is an incredible survey. And to show you, at the very top, I showed you the Hubble Ultra Deep Field. Took up the whole screen. This is the Hubble Ultra Deep Field in the same region. That's the thing I showed you right off the top. Just this right there. Like, I'm not kidding. It's the same thing. You can see as I go back and forth, it's the same galaxies. We are looking at a field significantly larger than the Hubble Ultra Deep Field. And if you're like, well, what about the Hubble Deep Field? Well, it's down here. There's the very famous 1990s Hubble Deep Field that launched a revolution in extragalactic astronomy, and it's just one tiny chunk of our full data. And when I looked at all these galaxies, it's like 500,000 galaxies in this. 500,000. We could very easily find real galaxies. I showed you a fake one earlier, just a couple slides ago. These are all real galaxies. So look, I don't see it in this filter. I suddenly see it in all these filters. I don't see it in this one and this one. I suddenly see it in all these ones. I don't see it here, here, and here. And by doing this, I can figure out how far away the galaxy is. This is a very far away galaxy. Very, very exciting. So let me come back to this diagram right here. Here is redshift, absolute magnitude, how bright it is, right? The same objects I showed you from pre-JWST. Well, if I want to show you results from a paper that I just submitted a couple months ago, I need to extend the x-axis a bit. And these are my sources. This is why you build JWST. They spent $10 billion in this telescope, and in large part is because we can go from just, a couple dozen galaxies to a statistical understanding of galaxies stretching back to a couple 100 million years after the Big Bang. There are over 2,000 galaxies in this sample. This is actually a conservative sample. I'm pretty careful about how I do my visual inspection, how I do my confirmation and stuff. I had the opportunity to do that. Other teams had to do it rushed, and so did not. Look, this is an incredible sample. The ones that are circled have been confirmed, meaning we've passed at some point their light through a prism to confirm it. And you can tell the ones that have been confirmed are generally the bright ones that are close by. But there are a couple exceptions. We're going to talk about it. I put numbers on some of the really exciting weird ones. There's GNZ11. GNZ11 is a weirdo. It's really bright. Really bright. We actually don't understand how GNZ11 came to be or what's going on. It could have a supermassive black hole growing up. This is a thing that will be studied for decades. This is a thing that if you were to come here, and you get excited if I were to come here to work here, and you were excited about being like, what are these galaxies like? Well, let me just tell you, they're there. Let's look at them, right? Let's look at their pictures of some of them. Here's some pictures of some of them. Every one of these is a real galaxy, generally at the predicted redshifts. And notice, they are not growing by themselves. A quarter of the sample, 25% of a sample of galaxies, the vast majority were never seen before, all from the beginning of time, are clumpy or elongated. They're not just growing like a little clump by themselves, they're 2 clumps or 3 together, right? This is very small compared with our own galaxy. Our galaxy is 100,000 light years across. This is 1/100th of that. These are tiny little things compared with the Milky Way, right? You can see 1.2 kiloparsecs, which is 1.2 thousand parsecs. Parsecs about 3 light years or so. So this is, much, much, much smaller than the Milky Way. But this is how the Milky Way grew. It grew in little chunks, combining with other little chunks to eventually form larger disks. But we're not seeing the disks here. We're just seeing the building blocks. Essentially what that picture I just showed you is a Lego set for the universe. And I poured the Legos out on the table, and some were already stuck together, and some were looked like And that's what we're seeing. The galaxies being stuck together such that eventually, if you were to watch a Lego being built, your Lego galaxy, it would start with these little building blocks that would form the larger thing. That's what we're seeing for the first time ever. And we've done an amazing job confirming some of these. So this is a picture where I'm kind of zooming in just on the most distant objects. Like I had a whole bunch of objects over here on the left I'm not showing you. Every one of these circles represents, as of this talk, the farthest confirmed galaxies. There might be a couple I'm missing, but if you go to like Wikipedia's list of furthest astronomical objects, these are the ones on there. The gray points are my ones that I'm predicting, my prospective candidates. All of these. I discovered most of the red ones. This one, I did not discover GNZ11, that was Pascal Osh. I also didn't discover this, and I think I didn't discover this, but most of the other ones. And the purple ones are from other teams. But look, we're seeing and sampling a pretty biased, bright end of things. The big question is, why have we stopped here? Why can't we find this? That's one of the big outstanding questions. Let me show you GNZ11's spectrum, its confirmation spectrum. This is one of the most impressive spectra I've ever seen. Jane Rigby, who won a Congressional Medal of Freedom from the president a couple years ago, working on JWST, said just the other day at the University of Arizona, she's thinking about getting this tattooed on because she was so blown away by this. The JADES team got this spectrum in 2023. I just remember on the telecom the first time that it was shown. Like you could just hear the jaws hitting the table. Because this is showing you, from when the universe is 440 million years old, that this is an incredibly complex galaxy. There is carbon, there is nitrogen, there is magnesium, there is oxygen, helium. There is, like all of this galaxy from the beginning of time. The universe has only had 440 million years to be this complex. Again, this is the equivalent of me being like, well, I took my first picture of an ancient Roman soldier, and the picture shows him looking at an iPhone, and you're like, how did he get an iPhone? How did they have an iPhone in ancient Rome? How did they have magnesium, carbon, nitrogen, in these abundances, in these ratios? So many papers were written, this is just a small subsample, about this one spectrum. It blew my friend Peter Senchina, who wrote this paper in 2023, he didn't even have time to wait for the spectrum to come out in the paper. He digitized it from the plot in our online version, just so that he could start analyzing it and going, what's going on with this object? And this was just the beginning, because I identified 4 galaxies in our early observations that were even farther than this. These are their 4 objects. I identified them. It was a crazy time. We put them on slits. We got the spectrum, and every one of them came back at the distance I predicted it. This is Babe Ruth going to bat, pointing at the wall 4 times, taking 4 swings, and hitting home runs exactly where he said they were. Boom, 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 boom. This object right here, when it was discovered, was the world record holder. If you go to a library right now and pull off your Guinness Book of World Records from 2025, I think, or something, this will still be listed as the farthest galaxy. It's been eclipsed a couple different times since then. But it is, in fact, it was the record breaker, the first farthest galaxy JWST have ever seen. The farthest galaxy humans have ever seen, light from only 325 million years after the Big Bang. These ones, though, didn't show all the spikes you saw here, all the heavy elements. They were relatively pristine. A couple had a little bit of that, but they were pretty pristine. Now, these are noisy data, so we've gone back and gotten deeper data. This is one of the deepest spectrum that JWST has taken. This is 75 hours from a paper I wrote a couple years ago. And even there, I can kind of barely see some spikes from oxygen and neon, but hardly anything else. Maybe some more neon here, but really it's very, very limited. And this image is deep, the spectrum is deep enough, it's long enough that I should be able to see more. But this is telling you that the universe between, because this one is only 413, between 413 and 440 million years was doing a lot of producing of heavy elements. But we're starting to march back into a region we're actually starting to not see as much. The universe is more pristine, exactly as we predict. Because it's got to take time. If I told you that oxygen requires a star to explode and give its oxygen up, man, the fact that we're seeing oxygen means that some stars lived their entire life before 413 million years had gone by in the universe's history. If the universe were Star Wars, the 2 hours of Star Wars, the oxygen that gave up, the stars that gave up their life to make these oxygen you're seeing here, those are like the stormtroopers that die in the first 2 minutes. It's very far back in time. Here's JGSZ 13, one of the record holder. No lines, no complex lines in 56 hours of spectroscopy. This object is actually very difficult for us to understand when we do simulations and stuff. But after this, I wasn't done. I wanted to continue looking for really far galaxies, and I found this galaxy right here, JADES GSC 14, which was very weird. You can see that it's different than the other ones in that there's like a neighbor. This is a kind of an annoying neighbor here. And GSC 14, when we first found it, because of the neighbor, everyone said to me, Kevin, this is a trick. Don't think this is a real distant galaxy. It looks like it is, but the neighbor is part of the neighbor. Da, 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 da. And we eventually decided, me and my former grad student Jake, we gotta pressure the JADES team to observe this again and take a spectrum. When they got the spectrum, me and Stefano Carniani wrote a paper together in Nature that was, congratulations, we actually broke our own record. Meaning, by the time that the Guinness Book of World Records had come out saying that we had discovered the farthest galaxy, I'd already broke my own record with this. GSC 14, seen 294 million years after the Big Bang. The first galaxy confirmed before 300 million years, and it has carbon in it. Carbon. It's also enormous. It's not just a little nugget. It's huge. It's way, way bigger. These blue dots show that it's way, way extended. It's a really crazy object. And my grad student Jake also came to me and was like, did you know that this object's even brighter out at longer wavelengths? So you can see here a picture of it, exactly as I was showing you in the last, right? There it is in the stupid neighbor. I shouldn't say stupid. It's just annoying to me because if we hadn't had the neighbor, we would have found it a lot earlier. This is a picture at 7 microns where it's even brighter than it is at 3 microns. So the 3 micron point is this one right there. There's the 7 micron point. It's like, 40 nanogenskis to 70 nanogenskis. It's like very bright. And we both did the math when he showed me. He came into my office. He's like, did you know this? He shows me on his laptop. And we both look at each other, and we do the math in our heads, and we go, that could be oxygen. If this galaxy's at the distance we think it is, that could be oxygen. That could be booming oxygen, only 294 million years after the Big Bang. And so we got a spectrum, one of the longest JWST Muri spectra. We got a spectra just last year, and it came back, and this right here is perfect evidence confirming the oxygen gas, the hydrogen gas, in this galaxy. This is the farthest we've ever detected a very famous oxygen line. This oxygen gas that at one point astronomers called nebulium because we didn't know what this could be. It's seen in nebulae in our galaxy in this ghostly, beautiful green color, and now we're seeing it at the dawn of time. The universe is a baby, and stars have already lived their entire lives and died and offered up their oxygen so that it can be in this galaxy. Other teams have found this at slightly lower redshift. Last year, my record was broken, thank goodness. It's hard to have a world record because you get terrified about when it's going to get broken. It was broken by another team who found this, MOM Z14. MOM stands for Mirage or Miracle. In this case, Miracle. They got a miracle. Mirage would be one of the ways you can get tricked by looking like a far distant galaxy, but not. And this galaxy is at 14.44, and it also has strong lines. And I bring this up. The person who did all of the analysis of the lines and the gases in this was my former graduate student, Raphael Wieding, who's at Max Planck Institute, so I still feel like I have some connection to this, even if I didn't analyze this galaxy. And so now we're finding these statistical samples of these galaxies, and what is it telling us? Well, it's telling us that our pre-JWST understanding, is a complicated diagram I'll get to in a second, the pre-JWST understanding was conservative. We really did not actually understand what we would see when JWST was launched. This is a thing showing, once again, redshift, so how far back in time. Right, I just showed you one of redshift 14.44, so we're looking like 300 million years is around here, right? Like 400 and 500 million years is over at 10. Pre-JWST was all of the stuff in this gold region, was what we thought of before JWST, and now we're actually able to watch as this is the star formation rate density. So if you take a chunk of universe, how many stars are being born in it? The bigger the number, the more rapidly stars are forming. And I would hope that as we go back in time, we get less and less and less star formation because the universe is still forming. So think about this going right from the Big Bang all the way growing. We're seeing that we had predicted, there were people that predicted that this purple, this is from a simulation from 2020, that it would get, like kind of drop off a cliff. The galaxies came on the scene relatively late. But the data is all telling us, actually, no. We're going to continue finding these bright galaxies out here. We think that there should be a lot of them. So here's the questions that I'm going to look at over the next 5 years. We found these galaxies. That was the relatively easy part. I mean, it took 20 years and $10 billion to build a telescope to do this. But what are the actual farthest ones? In my sample, you probably saw, I have predicted ones that are even farther. Are any of them real? How do these galaxies change in shape? This would be a thing that day one, some undergraduate walks in my office and they go like, how do I figure out how these things change and look at their shapes? And I just hand them a bunch of pictures and we go, let's write software to explore how the shapes change. How do we find this nebular emission, these gas lines, as we go farther in the past? There's ways in which we can do this just from images. And how can we refine our methods for finding the distances? And then there's more with ground dwarfs, all sorts of stuff, but these are the big problems. So let me just touch on this a little bit, because I know that I'm probably reaching the end of my time here. But what you can see right here is the same diagram I just showed. And notice it actually becomes pretty patchy out here. There's not that many objects. And the thing is that we're sensitive enough. The survey that I work on is sensitive enough to see these galaxies if they were there. But is the lack of objects real? Do we need more area? Are we not deep enough? I think we're deep enough. I think we may just need more area. This is interesting. I was not surprised when Mom Z14 took our record. But I've got enough of these objects. I'm wondering, where are these? Here are some of the objects in my sample that have not been confirmed, but are farther, hypothetically. This object could be a redshift 16. This one, it says 22, but that's because of the way that this is. I get really nervous because this is too nice to be real. I think that this is probably going to come out, and we're going to get a spectrum and find that it's a supernova, an exploding a star in a galaxy a lot closer, because that's a way they can trick us. Or it's something where we're actually seeing it here, like at 2 microns, and we should really. There's lots of ways the universe could trick us. There's lots of ways. We have to be very careful. The one that I have the highest hope for is this one. This object right here has this really gross name because we haven't confirmed it, so it still has its little telephone number name. I call it 1019411 because that's its ID in the sample. It's probably, if it's real, at redshift about 16.55, so 236 million years after the Big Bang. It looks pretty good to me. It even has a little bit of faint, here, which really helps sell it. And we took a spectrum, really not a great spectrum, but we took a spectrum of it. It's here. It's the yellow we're seeing barely here. And you can see that it agrees with a model at that redshift, right? The actual best fit is this red one, but it's, I don't know if I buy that. I think it's, Now, I published this not on a paper claiming, hey, give me the Nobel Prize, I found something even farther. Oh, I broke my new record, call up Guinness. I wrote this as part of a paper where I was like, listen, I know you're going to look at this in lab, and I'm right, scientists have looked at this and they have lab. But this is an exciting object that I'm hoping we can get a better spectrum for. And when I say I'm hoping, another team changed their observational plan just a couple months ago to get a spectrum for this. And they have a spectrum for this. I've never seen it. I do not know. They're a Japanese team that's working on it. And I'm just waiting that one day they might write a paper saying, congratulations, we broke the record. We found the farthest galaxy. It's part of Kevin's sample. Or they've already proven that it's not. I don't know. I won't know until they publish it, or the data becomes public in a couple of years. But like for right now, I know that they shifted it because I saw my paper and thought, oh, we should go after this object. Another question I ask is, how do these galaxies grow? Here are some of these galaxies I showed earlier that have clumps. Jihao Wu, who's a graduate student at Harvard that I've worked with, wrote a paper where he realized in my sample, just by taking my sample and plotting where they lie on the survey, that there was what's called an overdensity. These are clustering galaxies from when the universe was just 400 to 500 million years old. Galaxies were already clustering into groups. We know that galaxies exist in these big clusters nowadays, but we're seeing the formation of these massive clusters at early times. And he got a cycle JWST proposal accepted just a couple months ago that would go after a lot of these spectroscopically. I would come to Fresno with some money from that proposal because I discovered these galaxies to help pay to analyze some of these data and some ancillary data. My favorite are the two that are right up in here because this is them on the sky. This is actually how far away they are. They're so close that if you put the Milky Way's center here, the sun would be over here. They are like, the Milky Way galaxy would be this enormous disk here, but these two clumps are essentially on a collision course to form one larger clump. And we're seeing them as they're forming, which is really exciting. And then finally, outside of JWST, we're about to enter a crazy time where we are going to be just so much data poured on us from a telescope, a couple of telescopes, including a telescope called Roman. And Roman is going to not go incredibly deep and only go wavelengths out to like half of where JWST can look, 2 micron, 3 micron, but it will have an enormous area. And so it will be shallow and wide as opposed to these deep pencil things. And so what you're seeing here is my same diagram. Everything above these lines is something that Roman can see and Roman can observe. And so Roman would get a bunch of GNZ11s over a huge area. It could not see galaxies, many of the galaxies that are above a redshift of 12, 13, 14, but that's what JWST is designed for. Instead, it can do incredible mature statistics for hundreds of thousands of galaxies. Remember I had 2,000, I was like really excited. They will have hundreds of thousands of galaxies for statistical analysis between out your redshift of 12 or so. It's very, very exciting. And so finally, you can explore JADES from your browser. You can go to this website and click Viewer, and it will bring up a Google Maps style interface where you can just scroll around. And you can, up here there's these little hamburger buttons. This one down here, you can click on it and allow you to put a little circle on every galaxy. And if you click that circle, it shows you a plot showing Kevin's predicted distance. I made all those plots. I've looked at most of these. At this point in my career, I can look at these galaxies and just tell you where it is in the field, which is really shows you how much I've looked at these objects. But it's a really amazing resource. It's really great to go and go like, wow, I wonder what's going on. Because you scroll around enough, you'll find weird things. If you find something weird, send me an email. I like to see what people find. I'll tell you if it's been found already. So here's the thing. I want to finish this. When Hubble first pushed into the Hubble Ultra-Deep Field, we began to see galaxies assembling over cosmic. We saw the early parts of this. We were missing the opening chapter of this story. And with JWST, we are observing galaxies less than 600 million years after the Big Bang. And what we're finding is not this simple, pristine gas. We're actually seeing diversity. We're seeing galaxies that are compact, have all these complex emission lines and nebular emission, and some are really extended, some are in clumps, some are chemically mature and complicated with multiple heavy elements just very early in the first 100 million years. Others are, starting the process of reionization and clearing the fog super, super early. We're seeing the galaxy formation at cosmic dawn, what we call this, was not uniform, but it was already complex. My work focuses on building a physically consistent picture of this epoch, combining deep photometric samples of images with the spectra-confirmed things, confronting systematics and how we figure out how far away these galaxies are, measuring their sizes, how complex they are, and understanding how galaxies assemble into these big cosmic structures. The next 5 years of my career, I want to focus on 3 fronts research-wise. I want to confirm and physically characterize even farther galaxies. I want to understand how they grow, complex chemically, by their shape, and also by how they exist within each other and in their environment. And I want to make the predictions, distance predictions, more precise, because I think there's a real need for better estimations of distances. We are, for the first time, exploring a universe as it's changing from the Big Bang in an amazing way. And the thing is I want to help build a coherent physical framework for how galaxies grow at cosmic dawn. We spent a century measuring how far back we can possibly see to here at JADES GSC 14. And the next step is understanding what we're actually looking at. Thank you very much. I'll take questions.
We have a few minutes for questions.
Yes. Any questions? Yes, in the back.
Maybe you mentioned it earlier in your talk, but what can you say about population 3 stars? That
So-
earliest population, or is the definition of a population 3 star being changed?
Yeah, so if you're unaware, galaxies come in 3 populations, named based on how they were discovered or whatever. But most stars around us they've gone through multiple epochs. The gas has been in stars before. But there's this hypothetical in simulations, and not hypothetical, it probably has to exist, set of stars that are only hydrogen and helium. We're called population 3 stars. And we think that they have to be really, really, really big and probably explode in these enormous supernova. And at the moment, we've never seen evidence for population 3 stars or their supernova. JWST was designed in part to help us understand that, but it has not yet. Now, there are some scientists who claim, based on the presence of specific elements, helium elements, that they're seeing the remnants of population 3 explosions, and that's the closest we've got. And there's an enormous amount of tension in the literature, because there's other ways in which helium, this is a very specific helium emission line, 1640, can be produced. But right now, the answer is, even with all of this, things are more complex, meaning that population 3 stars likely formed very, very early on and had a brief thing, and like maybe at the end of JWST's lifetime, in 20 years, JWST will see we'll be able to accumulate enough data to start seeing the remnants of the population 3 supernova, but it's very, very tough, right? We were stunned by how complex these are, because that indicates that the population 3 must have been pretty early.
Much more brief than we thought.
Yeah, exactly. Other questions? Go back.
Yeah, the line is that due to gas within the actual galaxy?
In and around the galaxy, yeah.
Okay, so not the intergalactic medium?
It's a little bit, there's some of that, and that will play a part, but the thing is that the intergalactic medium's at a different redshift. So that hydrogen gas is a different redshift absorbing, and so this is a thing where the cliff itself, the Lyman break, is mostly just because of gas in and around that galaxy. It's a really wonderful thing. The person who pioneered that technique of looking for galaxies this way was my advisor's advisor, who's at Caltech, Chuck Steidel. His student Alice Shapley was my advisor. So when I do this, I'm essentially like continuing on the tradition of my ancestors, my academic ancestors, who discovered this in the 90s. Any other questions? Come on, undergraduates. If you don't, I'll give you a question that you can ask me. Anyone? Yes.
The goods data, is
Yeah.
it far away from the galactic plane? Do you
Yes, it
avoid
has
the
to be,
galactic
because
plane?
you wouldn't want to look in the galactic plane.
Yeah.
Because the galactic plane has our galaxy, and the Milky Way galaxy would just get in the way. Like, if you've ever looked at a picture of like the center of the galaxy or in the galaxy, it's just stars. Like the reason the Milky Way looks like milk is not because of milk, it's because of the accumulated light of hundreds of billions of stars, all, and if you take a picture of that, all you see is stars. And I care about the thing behind it, which is the galaxies. I'm always joking with scientists who study things in our galaxy, like nebula and stuff, like, why would you take a picture of the galaxies with this nebula in the way? I'm like, Kevin, I'm studying the nebula. Get the nebula out of the way, see those beautiful galaxies. And if you look at early JWST images, many of them have galaxies in the background, which are so annoying to astronomers. So annoying. There's an astronomer at University of Arizona who studies debris disks. So he studies ancient disks like the Kuiper Belt, like the remnants of a solar system forming. And he comes to me, his team comes to me, and they go, hey, we just got this really cool data for this debris disk. But this blob in the debris disk, this blob, we think it might be an incredible baby planet forming, or it could be a galaxy. Can you tell us which one it is based on fitting? And I fit it with whatever data I had, and it perfectly fit a galaxy model. And they were like, oh, deflated. And then a week after they published that, another team said, yeah, actually, the star is moving in the sky. And if you look at where this was before, you could see the galaxy, and then it moved in front of the way and got this thing in the way. So you got to watch out for the fact that galaxies are everywhere. And so the good south and good north field are like, if the plane of the Milky Way is like this, they're looking up north and south like this.
In the graph towards the end where you showed that the models predicted fewer galaxies at
Yeah.
far redshifts, and it turns out that there's more. Does that have implications for like how gravity works or anything?
No, it mostly just has, like, you can see that like the uncertainties of this purple are like enormous, right? Like Peter Brucey's universe machine, and they're mostly driven by the fact that Hubble was limited in its area and stuff like this. But mostly what the major thing is that we're wondering why there are so many bright galaxies at this time. Some, like, this goes back to this diagram. Like, there's actually quite a few bright galaxies, more than we expected. And that probably has to do with the fact that galaxies grow in a different way than we thought. They don't just like slowly get more and more stars. They go like starburst and then like no, we call it bursty star formation. So the star formation goes up and down and up and down. That's the big thing. But really, on that diagram, that has nothing to do with gravity as much as it has to do with how quickly structure can form. Dark matter was already in place in these pools, and we're starting to get, and things were forming, and stars were forming, and they were having supernova and stuff, and that is in line with our predictions, right? Peter Baruzzi, who made that big purple simulated thing, he's at University of Arizona. I've talked with him about this, and he goes, oh, I can go back and tweak some stuff in my simulation, and it fits perfectly, right? there's a tension between theory and observation. My job as an observer is to piss off theorists, make them annoyed. So then they go twist their knobs, and they go, now I can fit your observations. And then they come back to me. And then they say, well, and I go, okay, well, if that's the case, then you predict this, and then I go find that. And then it feeds back, right? I love to give theorists something that they've never seen before. Here's a question for the undergraduate. Some undergraduate asked me this question. I want someone to ask me this question. Raise your hand. I'm going to tell you the question. Hey, Kevin, why is there a gap at redshift 10? Someone asked me that question. No one said. Raise your hand, please. Someone asked me, hey, Kevin, why is there a gap?
Hey, Kevin, why is there a gap in redshift 10?
Isn't that interesting? Why? This is a good question to ask. What a great question. There's like 3 people who are going to ask me this question. It's amazing. And this has to do with the fact that I am predicting the distance based on that break, that cliff. And this corresponds to if the cliff is between 2 filters. If the cliff is between the 2 filters, then I don't have any information because I'm, making a prediction. And between F115, F150, F190, F115, there's like a little bit of an uncertainty. So like if I go out, I wonder if I can do this. Probably not. Let's see. Can I stop this thing? Between 2 filters, like right, here, it's actually really tough to tell the exact redshift because like right here, all this is uncertainty. Right here, 9.4, 9.6, 9.7. Notice nothing changes. Do you see that the red points don't change at all? And I go like this enormous amount of distance. And so things suddenly, once this thing starts dropping a little bit, then the redshift goes, I know the redshift. And so you end up getting this big gap. It's artificial. It's artificial. And so but it's, I'm going to tell you, folks who are in the room, when you are seeing a colloquium, don't worry about asking a question. There's no such thing as stupid questions. And the way you ask questions is on a graph. If you don't understand something, you go, what's that? Why is that like that? Right? Like, why are there some objects? Why is it? Here's the other question to ask. No one asked me this. Why does that one have a little triangle? And that's that weird galaxy I showed you that said it was at redshift 21.99, and I'm embarrassed. I think that's wrong. I don't think that should be on there. But I didn't want to extend this whole thing out to show that one, so I hid it by just putting a little arrow saying, it's over there somewhere, don't worry about it. This is what scientists do. We we massage things a little bit. Like I believe in it. It's there. I believe it's an object we should look at. But I'm not going to put a giant blank space and put that there. I'll just put a little arrow there.
So if you interrupt me, I'm afraid we need to bring you to the dean.
Okay. All right. Thank you very much.